There we go. So a couple of resources would be From the Ground Up, Chapter 9, pages 227 to 256. That's a good section there to read for you guys if you want more information. First thing to understand is just wavelengths, frequencies. So radio waves are measured in length of their length of the wave. The wavelength is linear measurement of a wave. A cycle is the period of which the wave vibrates between its crest and its trough. Frequency is the number of cycles per second. The higher the frequency, the more cycles per second that occur. So, if we're looking at our different bandwidths here, so the ones that we're going to be most familiar with and most using are LFMF and then VHF UHF. Okay, so you can see LFMF runs from 30 to 300 and then 300 to 3,000 kilohertz. So that's 1,000 cycles. And then the VHF UHF is the same, 30 to 300 and 300 to 3,000 megahertz, which is millions of cycles. So that's the different bandwidths that they're running on. All right, so LFMF and HF frequencies can travel the greatest distance and are subject to the following phenomena. So ground waves follow the surface of the Earth and are subject to diffraction, so bending around obstacles. Sky waves travel up into the atmosphere and are reflected back to the Earth from the ionosphere. And the surface attenuation is the bending of waves due to a wave coming in contact with your surface and slowing down, causing the wave to tilt forward following the curvature of the Earth. So if you have the Earth and it's curved down here, you got your ground station, like an NDB or something like that. It would be a low frequency nav aid. There's your aircraft, so that frequency is actually going to bend over any obstacles or anything like that and get to your aircraft, or it's going to hit off the ionosphere and then bend back down to your aircraft. Okay? High frequencies are line of sight frequencies, so they do not follow the curvature of the Earth or bend around obstacles. They do not bounce between the reflecting ionosphere and the Earth. They require greater altitude in order to receive VHF signal at a greater distance. So the numbers that you guys are going to want to memorize for the test anyways, because they're going to ask for high frequency reception, what's the most accurate altitude and distance to sort of receive at. And if you're 50 nautical miles away, you should be about 1,500 feet high. If you're closer, that's fine, you can be lower, but that's just saying if you are about 50 nautical miles away, you should be at 1,500 feet. And that's because, we'll look at the picture in a second, so VHF is not affected by precipitation static, it's very quiet and reliable. So VHF stuff is more modern, the equipment so requires less power to operate, the equipment is much smaller compared to the LFMF equipment. So that's nice. But it has issues like this. So we're fine if we're up high enough and we're getting that direct signal. As soon as we go down behind an obstacle, whether it be a building, trees, mountains, any sort of obstacles, whatever, we're not going to get the same strength of that signal. So our radios are VHF radios, and so we notice this all the time. Like when we're sitting on the ground here and we're trying to get a ground signal, whether it's ATIS or whether it's ground or whatever, we're not getting a super strong signal, right? Sometimes it's super crackly, sometimes it's almost unreadable, because we look at all the stuff we have in the way, right? We've got all that big row of trees, we have a building over there, there's several things in the way, and so that signal from the tower is trying to get over to us, and it's got some stuff in the way. It's getting through still, it's just not getting through as clearly as it should be. But you guys will notice, as soon as you pop the tower frequency and hop up, even just that few feet of hopping up into the hover, that sometimes makes a pretty big difference. So you get a much stronger signal, and as soon as you guys get climbing out a little bit and you get a little bit of height, boom, that signal becomes way stronger, right? It's the same thing when we're out in the practice areas. You know, we're on one side of Sumas Mountain and somebody else is on the other side of Sumas Mountain. It's terrible static, right? We can hear them, but it's really bad because it's trying to bounce off stuff and get over to you, but it's not doing a great job at it. So. Okay, so radio beacons. We call this a non-directional beacon. It's an NDB. It operates in 190 to 415 and 510 to 535 kilohertz bands. And it uses en route navigation, or the uses of it is en route navigation, approaches, and final approach fixes. So what you can do with these things is you can actually use them, as we were talking about in our previous ground school, tracking from one nav aid to another. And so you track outbound from one, and then track inbound to another. Or like for Abbotsford, for example, we have the Abbotsford NDB, which is just a few miles that way along the approach to the runway. And so what you do is you fix into that NDB, and then you can shoot they call it an ILS approach with that NDB. Okay, and so what you'll have instrumentation in your aircraft that basically shows you if you're off track to the left or the right, or if you're off track if you're too high or too low. And so you just put those two needles wherever they happen to be, you put them centered with each other, and then you fly that glide path, that slope, all the way in. And it can constantly be sensing if you're left or right of track, or if you're too high or low of track. And they set that track up predetermined to say, you should fly at this glide path down to the airport kind of thing. And they test this on a regular basis. Nav Canada actually owns a business jet that cruises around. I don't know what else they use it for, but I know that's one of the big uses, is they actually cruise around all the airports. They shoot instrument approaches to all the airports, and they make sure that all their nav aids and everything are accurate still. And so they're constantly doing testing on that. So, all right. So it's used in LF, MF airways and air routes. We talked about that. So here's the Cultus Lake NDB, and then this has a bunch of airways coming off of it, and so you could nav to this NDB and then off somewhere else. And there's the information that goes along with it. So this is a nav box here. In this case, it's saying that this is Cultus, so that's the Cultus NDB. There's the frequency for it, so it's 214 kilohertz. And then the identifier is LU, and then there's a Morse code. So when you tune this in to your ADF, so the instrument that you have in the aircraft is called an ADF, and it comes with a gauge that kind of looks a bit like a heading indicator, and then a radio stack essentially. And so you can tune in kind of like you would on a radio frequency, you can tune in this frequency. And then on the display, it'll show you LU, so you can see, oh yeah, I put in the right one. And then in your headset, you'll hear that Morse code. So you'll hear, the dot, dash, dot, dot, that, whatever. And so, so you'll be able to know that you actually tuned in the correct one. Okay. So ADFs are automatic direction finders. ADF instrument that interacts with NDBs. So this is what we were just talking about. It's the greatest advantage of the NDB, the range. So it's not dependent on line of sight like the VOR system. ADF is able to pick up stations at a greater distance, which is nice. ADF gauges are either fixed card or moving card instruments. And this is kind of what it would look like if it was inside your aircraft. Okay. So we have the fixed card. So nose of the aircraft orientated north, 0 on the card, and then you measure the relative bearing to the station. So if the station was over here, like the NDB was sitting over here, this arrow would point to 90, and so you would know, okay, my difference between here is what they call relative bearing. We'll look more at that. But that's the amount of degrees you need to turn to get to that station. And then the moving card allows the pilot to orientate the gauge the same heading of the aircraft, allows the pilot to calculate inbound or outbound tracks to a station. So we have a fixed card ADF or a moving card ADF, depending on what style you have in your aircraft. And on all your tests, they're going to be using the example of a fixed card ADF. And they'll always tell you that. A third ADF gauge called an RMI incorporates a gyro heading indicator on an ADF gauge. So it's just kind of getting into a more complex gauge, and that's what it'll look like there, the RMI. Errors of the ADF system, quadrantial error. So similar to deviation in the magnetic compass, it's caused by refraction, bending, or incoming radio waves by the structure of the aircraft. So there's always that kind of stuff. Minimum effect at the nose, tail, and wingtips. Error is less than 10 degrees. Oscillation to the needle. So the needle's not always 100% steady. Small oscillations of the needle indicate correct operation. And wide oscillations, so if it was really like back and forth like this, they call it hunting, and that's not good. That could be bad static conditions or a weak signal, or the aircraft is midway between two stations and it's trying to hunt one to the other kind of thing. So we have a night effect. So LF-MF radio bands produce ground and sky waves. ADF hones in on the ground waves At night, the sky waves are much stronger than in the daytime since they are reflected by the ionosphere. So it's kind of interesting that at night they're actually stronger and create more error. So random sky waves produce erroneous readings. We have the terrain effect, so coastal effect. So if you're along the coast between the ocean and the inland, as the radio moves past from the land to the water, the direction of travel changes. You have a mountain effect. In mountain terrain, the signal is reflected off the side of the mountains. We have ore deposit. So ore deposits will sometimes cause the needle to deflect off course. So all different types of potential errors. Ice and sleet. Accumulation of ice or sleet on the antenna tends to produce a false reading as well as reduced signal strength. Precipitation static, heavy rain or snow may cause static on LFMF bands. Static may be so severe as to interfere with pointing capabilities of the needle, and precipitation static can be lessened by slowing the aircraft. Thunderstorms contain charges of static electricity also interfere. Lots of errors, as you can see, right? When are these things ever correct? I don't know. And lots of times the errors won't be dramatic, but they will be noticeable to some extent. In order to fly directly to an NDB, simply turn the aircraft so that the needle is pointing in the same direction as the aircraft. So remember that needle that we were looking at? You would just start turning the aircraft in that direction, that needle would start turning, and once the needle is pointing straight up, then you're flying straight for the station. So in the aircraft, these things are extremely easy to use. When we're sitting there looking at a test question, it's a little different on the other hand, and that's where we have to figure out how these things work. So, after passing the station, the needle will rapidly flip 180 degrees, right? So it's showing you, yeah, you're flying towards that station, and then all of a sudden, whoop, it's going to go the other way, and it's like, oh, it must be behind me now. I'm passed over it. Crosswind procedures. So the situation if left uncorrected, we've got the aircraft here, this is where we want to go, and we can see the wind is blowing in this direction. And so if you didn't do anything for it initially, if you had no idea where the wind was and you're in cloud and you're just flying, you're going to drift off track, and as you drift off track, that needle's going to start kind of pointing in that direction a bit more, and so you're going to have to, okay, I've got to continue turning. Now as you get closer, of course that error is going to become less because you can only go so far off track before you start getting back on track. So the ideal thing is if you know what the winds are already doing, you make a correction for that, just like we would with navigation, regular navigation, and say, okay, well I know the winds are from over here, so I'm going to correct a little bit into that direction, and then I'll just continue flying according to my needle, but I'm going to always have a bit of crab into that wind, right? And then it's going to be a lot less exaggerated like that. Okay, now we're into high frequency stuff. So VHF, Omni Range Navigation System, is what we call a VOR. And this functions in the VHF frequency band between 108.1 and 117.95 megahertz. Station outputs two signals. So we have the reference phase, and which is non-directional, similar to an NDB, and then the constant phase throughout is 360 degree transmitted at 30 times per second. Then we have the variable phase signal that rotates at 30 times per second, 1 degree for every 92.6 milliseconds, or microseconds I should say. Based on the phase difference between the two transmission signals, it measures the time that it takes from north basically to get around to the sweep of where the aircraft is. The time in between the reference is called the reference phase, and then that's going to essentially give you a radio. So we're going to see a picture in a second here. You have 360 degree useful radials, 3 types of VOR systems. So we have TACAN, which you're probably used to, because that's the tactical air navigation, that's military use. Then we have a VORTAC, which is a VOR combined with TACAN. And then we just have simply a VOR, which can also include VOR and DME combination. DME stands for distance measuring equipment, and so it just measures how many miles you are away from that station. And so not only will it give you a radio to say, hey, fly this heading to get to that station, but you're 23 miles away from it right now. And so that's kind of nice to be able to have that. So they'll show you a little picture here, essentially, or a little diagram, and it's basically saying this is what it's doing on a constant basis. So it's shooting out like 360 radials, and it's measuring the distance between or the time between north and where you are, and then it can figure out, okay, you're X amount of degrees away from it. Okay, this is what they look like on the map. So, on the inside here we can see this is our nav aid. It always has this compass rose around it, which is really nice, because this line here with the little arrow is pointing to magnetic north. So it's really nice to have these on the map, because then we can actually see, without even looking at a line of variation, we can just see automatically, okay, this is north, so this is 60 degrees or whatever, and we could just use our pencil, and if we were looking at our map, we could say, hey, I want to fly that heading right there. We slide that over and say, oh, that's 60 degrees, and that's a magnetic heading already. So it's just easy for basic navigation. We use that all the time on our diversions. Same thing for these guys. This one's the Whatcom VOR in this case, or Vortac. And then there's the frequency 113.0. HUH is the identifier, and there's the Morse code. And in this case, because it says channel 77, when it has a channel associated with it, that's the DME that I was talking about. So that's the distance measuring equipment. So you could also tune in channel 77, and then it would give you how many miles you are away from it. So, when there's an airway, this is kind of what it would look like. So this would be a Victor airway, a VHF airway, and they just number it, so 495 in this case. So the disadvantages: VHF signal is limited to line of sight reception. At distances of 50 nautical miles, signal will be received at an altitude of 1,500 feet. Farther from the station, the higher the aircraft has to be. So they don't give you any other numbers, but you could use that formula to figure out altitude based on distance. Terrain effect error, reflecting of masking of the signal by terrain or mountains. Site effect error, so erroneous signals can be caused by objects in the vicinity of the station. Most VOR stations are equipped with an air-to-ground communication, which allows pilots to contact FSS on 126.7 or whatever frequency they tell you. So that's really nice. You'll look at the boxes and it'll show you on the top of the box what frequency you could actually contact FSS on. And so that's really nice. It allows a direct signal up to the station. At selected VORs, tape weather broadcasts are transmitted. So they're called TWBs or ATIS. So you can actually get some of these places, you can actually get a weather observation. VORs can also be used for DF assistance. So DF stands for direction finding. And so sometimes you can use these for, like, you would call up FSS and say, hey, I'm lost. Can you help me out? And so him using his instrumentation can actually say, okay, you should fly a heading of whatever, and actually get you pointed in the right direction to go somewhere. So, TACAN or VORTAC. TACAN is Tactical Air Navigation, operates in the UHF frequency band. Primary and military system, combines functions of VOR and DME. The aircraft equipped with the DME equipment can receive distance information, requires special equipment in the aircraft. VORTAC combined with VORs and TACAN stations. Victor Airways. So, networks of VHF airways which make use of the VOR stations are arranged across Canada, numbered like highways. We've already looked at these guys here. So there's the Victor Airways depicted on the charts by a shaded outer line, which is outlines the limits of the airway. So here's the shaded outside line. And so in this one, it's 4 nautical miles from here to here and 4 nautical miles from there to there, because this is a high frequency airway there. Okay. Yeah, there you go. 8 mile total. So we've already looked at this, but we'll look at it quickly again. So the high frequency nav aids, it's 4 nautical miles from here to the outside, and it's 4.5 degrees for the splay. Whereas the low frequency nav aids, these guys, is 4.34 nautical miles to either side and a 5 degree splay. So slightly different on those ones. The best way to think about this, I sort of have a system that is a full circle system that works to be able to figure out the two different types. Now, as long as you know a couple factors, then you can figure this whole thing out, okay? So factor number 1 is you have to memorize these numbers. You have to know that it's 4 miles versus 4.34, and you have to know that it's 4.5 degrees versus 5 degrees for the splay. And then you have to know that low frequency nav aids are less accurate. We've just seen that. They're less accurate than high frequency nav aids, okay? And so if you remember that, the two different lines that you'll see on the map, grab this map here for a second. So we have these lines, which are dark and narrow lines, versus these lines, which are more shaded and they're wider lines, okay? So here's my thought process. If it's a narrow line, it's got a narrow width for the airway, okay? The narrower the width, the higher the frequency, because the high frequency ones don't need as wide of a width, right? So these guys, I know because they're more narrow, it's a high frequency nav aid, so it's a VHF UHF airway, right? Then I also know, because I know that then, I know that it's only 4 nautical miles on either side, and it's a 4.5 degree splay, right? And it's going to connect high frequency nav aids, which are usually VOR to VOR, okay? Whereas this guy, on the other hand, it's wider, the line is wider, so therefore the width of it is wider, 4.34 nautical miles. It's got a 5 degree splay, and it's going to connect low frequency nav aids, which is NDB to NDB. So just knowing those couple little factors means you can just look at a line and you know everything about it, essentially. All the important stuff anyways. Okay? Cool. So VOR instruments, OBS. So that when we talk about an OBS, that's this thing here, and that's just a knob that you can turn, kind of like when you guys set your heading indicator. You know, you can push that in and do your turning, right? This is the same thing essentially. Essentially for this, and it's just to be able to select a radial. So you can turn that and be able to select a radial that you want to fly to. So we, in this case, selected the 340 degree radial, so we've spun it until 340 was at the top here. Then we have what's called a to from indicator, and that just indicates whether you're flying towards the station or away from the station. Okay? And in this case, here's the to from indicator. Sometimes they're a little more obvious, they're on the side and they'll say to from or whatever. There's different options for different types of gauge. And then these are the needles we were talking about for the glide path. So this one here is showing you that you're off to the right or the left, and then this one here is showing you that you're too high or too low. So if it's up here, you're too low. If it's down here, you're too high. So it'll always show you in relation to a flight path. You know, if it's up here, it's saying you're down here looking up at it, you should climb to get back level. If it's down here, you're up here looking down at it, right? Same thing with this guy. It's pointing in the direction that you need to fly to get back on track. So this one is saying, hey, you need to turn right to get back on track. If it was over here, you'd need to turn left to get back on track, or fly left or fly right. So, okay. CDI, this is what they call the CDI needle. CDI stands for course deviation indicator. Okay. This would be your radios that you'd be looking at. There's your VOR instruments. Okay, so this is kind of a simplified version here. You have a to from indicator, there's your OBS, there's your CDI needle. To use, tune in the proper frequency, identify the station, test your equipment, set the appropriate radial by rotating the omni-bearing selector, the OBS, which causes the course deviation in the CDI to move. And that's basically it for that. Okay, so if you were over here and you wanted to fly to this station, what you would do is you'd actually go 50 degree radial to a heading of 230 degrees. So if you were over here and you wanted to fly to this station, you'd actually be flying a heading of 230 degrees. Okay? So depending on it, you have essentially two different sides to this radial. You have a to side and a from side. We'll look more at that when we get into the questions and stuff. So if we selected, so if we selected the 230 degree radial, if we were over here, it would show 2. And as soon as we switch over, like as soon as we pass over the halfway mark right here, then it'll flip to a from. So it's showing you, just want to see if it, it didn't show the 2. Oh yeah, there's the 2. Yeah, there's 2. And then as you fly over it, so now when you get over top of it, it'll look like this. It'll just go to a red crosshatch little box. And then once you get past it, then it'll show from. Right there. And then this thing will show 230 on the top and 50 on the bottom. If you were to turn around right now, then it would flip. It would be the 50 on the top, the 230 on the bottom. All right. And then this thing would flip as well. So it would, if it was saying 50, it would be 2 until you get over it, and then it gets from on this side. Okay, triangulation. This is fun. So what triangulation is getting a from indication. So using the same method that we just looked at, if we can get a from indication from 2 stations. So I got a station here, I got a station there. I'm going to spin both of them until my, I'm going to spin both my OBSs until I get a from indication. I'm going to keep spinning until that CDI needle centers. Once the CDI needle centers, then I know the track, like whatever number it says on the top, that's the track that I'm on. That's the line that I'm on, okay? So in this case, I spun it and I got a from indication, and this needle has come to center, and let's just assume in this case it's 98 degrees. Now this would be magnetic, here's magnetic north. So you draw your line on the map at 98 degrees off of there, and that's going to be that means you're going to be somewhere on that line right there. Then you do the same thing from this station. You spin it until the OBS, or you spin the OBS until the CDI needle centers with whatever indication you get there. You draw your pencil line on there, and where those 2 lines intersect, that's where you are. Okay? So you could be lost somewhere, have 2 stations, tune into each one, and draw your lines on the map, and you figure out exactly where you are. That's kind of cool. They call it triangulation. Okay? Triangulation examples. Yeah, you could do those if you want, but we'll skip over that right now. Okay, relative bearing, definitions. So this is something that you're going to want to start writing down here now. We need to write down MH stands for magnetic heading. You don't need to write down this definition stuff, but you just need to write down MH equals magnetic heading. And this is something that you guys are going to use for the next 3 weeks or so. So you're going to want to know this really, really well. Okay, so that's pretty easy. Magnetic heading, that's the heading that you're flying magnetically, right? So you're cruising along, whatever your compass says, that's what it's. That's what the magnetic heading is. It'll be quite different from the magnetic ground track if a crosswind is present. So you might be actually pointing somewhere totally different, right? You're trying to go somewhere different. Now the relative bearing is the bearing to an object or nav aid relative to the direction of the aircraft is facing. So put down RB for relative bearing. And relative bearing means the amount of degrees that you need to turn to the right, it's always to the right, never to the left, always to the right, from the nose of the aircraft to get around to the station. Okay? So if, we don't have an aircraft here, but okay, sweet. So if this is my helicopter pointing like this, that's my magnetic heading. And then the amount of degrees I need to turn to get to the right to point to this mouse is whatever. And then, you know, if I'm looking at this, that's about 90, so it's probably 100 degrees. So that 100 degrees is now my relative bearing. Okay? That makes sense? Mm-hmm. All right. Then we have what's called an MBTS, which is a magnetic bearing to station. That's exactly what it sounds like. It's a magnetic bearing for if I were to turn now to this station, and I were flying towards this station, what's my compass going to say? That's my MBTS, okay? So, it's a magnetic track or bearing that I need to fly to get whatever station I want, a POR or an MDP or something, okay? So now, we need to go to, let's write down a formula here. We need to go to, I don't know, grade 6 math or something like that, to when we first learned about formulas. And so we've got a 3-part formula here. So let's write down MH plus RB equals MBTS. All right. Now we can have a couple different variations of this. We could say MBTS minus MH is going to probably equal RB, right? Or MBTS minus RB is going to equal MB or MH. That makes pretty good sense, right? So this is really, really basic formula stuff. Okay. One more thing that we need to write down is something called an MBFS. So if a magnetic bearing 2 station is an MBTS, what do you think an MBFS means?
From station.
Yeah, exactly. So how do we figure out an MBFS?
If you knew the reciprocal of
Yeah. So as long as we have an MBTS and then we add or subtract 180 degrees, then we get an MBFS. Okay? Cool. Those are all our possible options. All right, so now here's our example. So they're showing that track up, so like this is north, okay? And so now they're showing that the magnetic heading of the aircraft is 30 degrees, okay? Now from the nose of the aircraft it's 0 though, like the aircraft is theoretically pointing at 0, but it's magnetically north. But if I'm talking in relation to relative bearing, I go from the nose of the aircraft around to the right, and is it going to draw it on here? There we go. Around to the right until I get to my station, which is over here. Okay? So now in this case, we've turned 270 degrees to get to our station. So what am I going to do? I'm going to go my MH, which is 30, plus my RB, which is 270, and that's going to equal an MBTS, which in this case will be 300. Everybody's okay with that?
Yeah.
Okay, cool. And there it is. Other combinations, we just talked about that, we talked about that, and we talked about that. Okay? Everybody's cool with those? Okay, so here's a typical relative bearing type question that you'll get. In this case, it's in test 3, question 89. So if you guys get test 389 out of our practice exams, then that's this is the question that you're going to have here. So it says, while maintaining track on a heading of 188 degrees magnetic. Now let's pause here for a second. Whenever we're reading these questions, I find you sit there and read the whole question and go, I'm lost. I don't know what I'm supposed to do, right? So what I do personally is I just start identifying information while I'm reading. And then I'll pause, I'll go, oh, I know what that is, and then I'll just jot it down. I don't know if it's useful or not, but I'll jot it down, and then once I get to the end of the question, I'll figure out if I need it or not, okay? So I've just figured out, while maintaining track on a heading of 188 degrees. Magnetic, what is that? It's an MH, right? So I'm going to jot down MH 188, all right? Now it says the fixed card ADF, we know what that thing is, right? That's the gauge that we're looking at in the aircraft, is tuned to the Clear Lake NDB. So we've tuned that thing in, we've put in our frequency and stuff, and it goes root and shows you an arrow pointing to the Clear Lake NDB. Now, it says the relative bearing crossing the center line of the red 6, so that's an airway, the red 6 airway, would be what? Question mark. Okay? So what are they asking for? They're asking for a RB. The only issue is that we need 2 pieces of the formula to get the third one, right? So therefore, there must be a way to figure out that third piece, which is what? What are we missing?
Red 6.
The
MBTS.
Yeah, we need the MBTS to figure out the RB, okay? So because they told us that we are over the center line of the red 6 airway, we can figure this answer out, okay? So, node and airway, we've talked about that, and here's our airway here, and I think they're going to show us an example. Okay, here's our example. So we're going from the Ranger Camp to Cordova to Winnipeg, I believe it is, and here's the R6 airway. Now the beauty thing about airways is on the airway itself, it's actually going to show you what the heading is, the magnetic heading, if I was flying this direction or if I was flying that direction. Okay? Now that's really cool because if I'm here, if I'm here and I need to fly to Clear Lake NDB, which is here, guess what? I have an MBTS. That's a magnetic bearing that I need to fly to get to that station. Okay? That's really cool. Now, if I didn't have these numbers, which I do, but if I didn't, how could you figure out what the MBTS would be of that line?
On the chart?
If we had a map out right now, and we were looking at this airway. How would I figure out what the magnetic bearing to that station would be?
Well, you need like a protractor,
Okay.
you use the compass or something. Yeah.
Okay, so you're on the right track. Yeah, we're going to use our protractor.
All right.
Then we're going to figure out a heading.
Line it up with the.
Yeah, we line that up. That's right.
Yeah, and then you just find the airway and go. Okay, here's the airway. Look, there it is.
Perfect. Okay, so now we've got a heading. Is that heading true or magnetic?
True.
Ah, because we use this thing, and this thing we can see, so it's got to be true, right? So how do we get magnetic now?
You have to take
Subtract your variation.
Yeah, exactly. Add or subtract, right? So we're going to look at our map. On our map, somewhere near there, we're going to have a line of variation, and it's going to say east or west. And so we're going to say, well, if it's east, we're going to subtract it. If it's west, we're going to add it. So whatever the degrees are, 13 degrees, 20 degrees, whatever, east or west, we're going to add or subtract that from our heading that we just calculated, and then that's going to give a magnetic heading. That should equal or be very close to this number right here. May not be exact, depending on where this airway has chosen to use its line of variation, and which line of variation we chose to use. They might be a couple, 3 degrees different or something, but they should be very close. Okay, so that being said, we've got this number right here, so that makes our math really easy, right? We take the 282. Okay, so we got all that figured out. I'm just going to do it here. The formula. So 282, which is a magnetic bearing to station, minus our magnetic heading, which was 188, is going to equal 94 degrees. From my nose of the aircraft, all I got to do is turn to, from the nose of the aircraft, I have to turn 94 degrees to the right to get to that station. Okay, but my heading that I should be flying is 282 degrees magnetic. That make sense?
Mm-hmm.
Pretty easy, right? It's easy when you have somebody sitting here explaining it to you and drawing it out and saying, okay, this is what it's supposed to look like. It's much harder when you just sit there and read the question and you kind of go, what am I supposed to do now? So what you guys will notice is the first time you go through these tests, you'll get these questions and you'll just be stumped and you'll be like, oh, shoot, how does this work? Help each other out. Some of you, I guarantee some of you are going to pick it up like this, and some of you are going to really struggle with it. I was the one that struggled with it, and the guy that I was studying with picked it up really fast. And so we'd study together, and he'd be like, I don't know why you're not getting this. And I'm like, I don't know, I can't figure it out. And it took me till the end of the course to figure this stuff out. And even like when I did the written exam, I could get the right answer, but I didn't fully understand it. And it took me a while to really understand it. But
on the question on the test, so it would have some sort of diagram with that 282.
no, so it'll give you, for the test, they give you a map, a physical map,
So
and they give you a trip. And so like the trip, for example, in this on this test, the trip that they gave you is from flying a helicopter of whatever type from the ranger camp, and they tell you a coordinate for that, to Cordova to Winnipeg. And so they say you're on track from the ranger camp to Cordova, you're over the Red 6 airway, however they word the question, right? You know, your magnetic heading is 188. You know, what's your relative bearing to the Clear Lake NDB? So, yeah, so it'll be on the test. You'll have a trip that you're gonna be using for all sorts of questions. Yeah.
All right.
So, is that making sense?
Mm-hmm.
Yeah. Cool.
I would just use a compass. Can't you use a compass for this? I'd rather carry a compass in this round anyway. But just kinda, you line your map to north,
No.
and then you orient your compass along the line you want to fly, and that gives you your bearing.
Theoretically, I guess that could work. Yeah.
It does work because I've
Yeah.
done it on canoe trips and stuff.
Yeah, yeah,
Like,
yeah.
that's how they teach you to orient you.
Okay.
But
Yeah.
I wonder if you can. I don't see any issue using it in these two.
Probably not. And may not work so well in a helicopter. I'm not sure. Just because you're well, I mean, yeah, I guess if you're steady flight, but I don't know. It's good. Yeah, good idea though. Okay, so they're going to give you another example here. This is a different type of question now. They call this intercepting radials. Okay, so we just talked about flying on a radial to a station. But what if I wanted to intercept that radial? How would I do that? So in this case, it says you're flying a heading of 70 degrees magnetic. Okay, so here's your aircraft. You're cruising along on a heading of 70 degrees magnetic. The magnetic bearing to a VOR is 300 degrees, okay? So from you to the VOR, it's 300 degrees. So you just grab your protractor, you draw your line and say, okay, somewhere along this line here is my VOR, okay? So you know that it's over here somewhere. You plan on intercepting the 40-degree radial. Now the radial, of course, has to be coming out of the VOR, so it's this radial that you want to intercept, all right? So that's the one you want to intercept it, and you want to intercept it at a 45-degree intercept angle. So maybe the tower said you're wanting to intercept this radial. They say, okay, intercept the 40-degree radial at a 45-degree angle. So that's why you specifically have to intercept it at that angle. So what do? So on what magnetic heading should you fly to intercept it on that radial right there? First, draw a picture to help visualize the situation. That always really helps. Next, establish where the aircraft is in relation to where the needle, in relation to where it needs to be. So example, is it left or right of where it needs to be? So in this case, it's to the right of where it needs to be, right? It needs to be out over here. Okay? In this question, the aircraft is right of the desired radial. So solution, a left turn is needed to intercept the desired radial, correct? So we need to turn left to get onto this radial. So therefore, what we do, it says, but wait, what kind of intercept and magnetic heading is needed? So that's what we're trying to get to. For our question, we want to intercept the 40-degree radial, a 45-degree intercept. Therefore, since we have established that a left turn is necessary, we subtract 45 degrees. So you always subtract the angle that you want to intercept at from the radial that you're trying to intercept. All right? To get our new magnetic heading. Now, if we had to turn to the right to intercept, if the radial was down here somewhere that we're trying to intercept, we would have to add. So if it's to the right, we add. If it's to the left, we subtract. Okay? So in this case, we're going to take 40 minus 45 equals?
355.
There we go.
-5.
Yeah, exactly. So I was waiting for the -5 because in a revolving circle, we can't have negative numbers. And so -5 turns automatically into 355. Yeah. So our answer in this case would be 355. And if we flew a heading of 355, as you can see, that would intercept us at a 45-degree angle.
So you got to be able to do all this head math essentially. Yeah, they could potentially.
Yeah.
I mean, at some point, if I'm flying with this stuff.
Yeah.
Intercept this at this.
Exactly. Yeah.
And I'd be like, what are you talking?
Exactly. Yeah.
But it's like they'll throw in information that isn't needed.
Sometimes they will, yeah. Which sucks, yeah.
This
On
one,
the test.
the bearing to the VOR is irrelevant.
Yeah.
Exactly. Well, it isn't because you need to know that the station is over here as opposed to over there, right? So that's the only difference. Because if it said the radial to the VOR was 60 degrees or something, then that would mean it would be on this side of you. Therefore, you want to intercept that radial, you need to turn to the right.
Yeah.
You have to add it.
Okay.
Okay. So this one kind of makes sense, yeah?
Yeah.
Now once you've intercepted it, as soon as you cross it, your CDI needle, like up until you get to it, the CDI needle will say turn left to get back on track. So you're like, okay, I still need to keep going. As soon as you get over top of it, that needle will swing centered for a second, and then it'll go to the other side and you go, ooh, I just intercepted the radial, and then that's when you turn to the right in this case, and then you'll probably end up tracking back and forth just a tiny bit until you get bang on, your needle's lined up, and then you'll just keep that needle lined up and away you go. Excellent. I'm just noticing, it's October 20th is on Thursday? Oh yeah. Of course it's on Thursday, that's exciting.
That's first thing in the morning? I know
It's
on
all
the
day.
email. Oh, it is?
Yeah. Yeah, check the email. It starts at, I believe it's 8:30 or 9 o'clock, something like that. And then it'll go until 3:30 or...
And it's in Langley, right?
Yeah, it's in Langley.
Yeah. So we'll just meet there.
Yeah, you guys can carpool if you want to
Yeah.
or whatever is best. Yeah.
Yeah.
So,
Probably should.
yeah.
It'd be better for you not to carpool.
Yeah.
Why don't you drive out here and then carpool out there, yeah.
Sounds good.
Yeah.
Excellent. Okay. questions there, just going over that. You dial in the Vancouver vortex and center the needle. You want to intercept the 150 degree radial to Vancouver at a 90 degree intercept. What heading do you fly? This is what the instrumentation is showing you. Well, it's not even going to work it out for you. I'll let you guys work on that one.
Okay.
Alright, that's that for today.
Alright.
Cool. So I think you guys have enough information now to actually get started on these exams.
Okay.
So maybe tomorrow I will get some exams for you guys to start working on. I think I have to make more copies because we usually only have a couple copies per exam. So there's 4 exams total. The way it works is you're going to do each exam once to begin with through the whole thing. Ideally, like because there's a bunch of you, you're going to be sharing exams and stuff. So it really doesn't matter which order you do it in, but what I want to see is that you go through all 4 tests before you do one test a second time, okay?
Oh, okay.
Because if you're doing 2 tests in a row, like the same test twice in a row, you're just sitting there memorizing it kind of thing, right? So we want to get the variety of the 4 different tests. Each test is 100 questions, multiple choice, okay? The first time you go through all 4 tests, it's going to be open book. And I highly suggest, kind of like the P-Star, I highly suggest that you guys use all the references we have, like the database will be really, really useful for this. Look up the questions, make sure you understand what the answers are. Because if you're just sitting there guessing, you're going, I don't know, I don't want to look it up, I'll just guess, you're never going to learn. You're never going to learn why that's the answer, right? You'll just memorize, oh, okay, that's the answer, and on to the next thing. But as you read it, you'll go, oh, okay, that makes more sense. And help each other out, too, as you go to different questions and stuff. It'll make more sense if you guys are talking it out. So look up the answers, get the right answer, then make sure you come to us at the end of every time you've done the test and get us to mark it. We want to keep track of how you guys are doing so that we can see the progress and stuff. So don't always be sitting there marking your own tests. Bring it to us, we'll mark it for you, and then keep track of that test. You can keep the test if you want to, but don't keep the test to copy it on the next time around. Just keep it so that you can refer back to it and say, hey, I got 75% the first time, and I got 85% the second time kind of thing, right? So you want to see how the progress is. So then the second time through the 4 tests, you'll do it all closed book. And so now it's a real telltale to see how am I doing? How much am I actually remembering? You'll probably notice that your marks are going to go down a little bit. Because obviously the first time is open book, so it should be a pretty decent mark. Usually it's not awesome, it's usually in the 70s or something like that. Then the second time you'll probably see your mark drop down a little bit because it's closed book. However, it'll go way faster. Because the first time through the 4 tests, it might take you like a full week, maybe even a little bit more. Because each test will be at least a solid day plus a little bit maybe. And but then the second time through, you're only relying on your brain, so it might only take you 3 to 4 hours to go through a test. And then you'll do all of them a third time through, and by the third time through you should be getting into the 90s, and we want to see consistently in the 90s for all tests before we send you over to do the written. The third time through, again, of course, is closed book, and then you're checking your answers to see how, or your progress to see how you're doing. If for whatever reason you've gone through it 3 times and you're not in the 90s, no problem, just do it again. We've had some people, it just takes more time. I don't care how many times it takes, but it's going to get faster every time. Like the third time you go through it, you'll be ripping through a test in like an hour and a half. So you can do 2 or 3 tests a day pretty easy. So yeah, the first time through, you're going to slug through it. Second time is going to go quicker. Third time is going to go real fast. So,
Right on.
process makes sense? Excellent.
And we're not working on them communally, we each get our own copy.
You each get your own copy, yep.
we do.
But you are welcome
Yeah.
to, if you guys have the same copy or something, you're welcome to going through it together and stuff like that and asking each other what answers you got and why and whatever. There's no issues with copying off each other as long as you're not just sitting there looking over the shoulder of the other guy and marking down the answers. Like, if you're going to work together, it's for the sake of learning better together.
Yeah.
Because I firmly believe that 2 or 3 people talking something out and saying, no, I think it's this, and oh, why do you think it's that, and explaining, okay, I don't get it, why is it like that? You're going to learn 10 times better than one guy sitting there by himself just trying to figure it out on his own. So, and then again, same thing as the P-Star and everything else, the order of progression for how to find the answer and stuff like that. You look at it, You look at the resource, the database is going to be probably the quickest, best reference for you guys. If that doesn't work, look it up in the actual reference, like the CARS or the AIM or the CFS or wherever it happens to be. If you still don't get it, see if one of the other guys knows the answer, and then if you still don't get it, then come and ask me. Sounds good?
Good.
I guarantee you though, there will be lots of questions where you guys go, either we haven't learned this, or I don't know how to do it, or whatever, because there's still a few things that you guys haven't learned. If it's something that's just foreign to you and try to look it up and either you can't find it or it doesn't make sense, come and ask one of us, please, and we'll give you the explanation of why it's like that. Because it's way better for me to give you a 5-minute explanation than you to sit there digging for 2 hours trying to find the answer and still not getting